So in the previous lesson, we saw how we can trace in detail the algorithmic information trajectory of objects and events evolving over time. Here we will see that we can move from being observers to being drivers of how systems can change. For this, we will introduce a causal calculus based on algorithmic information dynamics. This is based upon perturbing objects or systems according to a sequence of interventions that lead to different possible trajectories. For example, let S be a non-random binary file containing a string in binary, such as this one. Clearly, S is algorithmically compressible, with, let's say, PS, the program that prints the string, being print 0131 times, which is a short computer program generating S. And now let S prime be equal to S except for a bitwise operation on a bit position number 24, for example. So bitwise not means basically that we flip the bit. So this is a resulting string. A short computer program that generates S prime can be written in terms of the original program that prints S. That can already account for most of the string except for the perturbed bit, which the new computer program has to account for. A candidate program can be a program P of S prime equal to print 1011 times, followed by print 3 zeros, followed by print 1020 times. So clearly the length in binary of the new computer program generating S prime is longer than the original computer program generating the non-mutated string. So we have that the relationship of their algorithmic complexity C is precisely the algorithmic complexity of S is strictly less than the complexity of the mutated string for this case. And this is also true for any single bit mutation of S that makes S a little bit more complex because the original one was already very simple. Notice also that we have here induced a point mutation in the form of perturbing a bit and flipping it from its original value. But if this sequence were a dynamical system, all the point-wise mutations could have been state transitions in a dynamic space. So these mutations are also covering the different 1-bit possible orbits or trajectories of this object, and we can cover in principle many more by continue making perturbations. So not only this is a causal interventionist calculus, but also considering is a way to consider all the possible changes of complexity of the different orbits of the same object. Perturbations can be of two opposite types when it comes to changing the complexity of the underlying model explaining the data. One kind are the perturbations that move an object towards randomness, and the other kind is the type of perturbations that move the object away from randomness. To illustrate this, we have this example. The kind of perturbation to be applied will be, again, bit deletion, and the object to start with will be a binary string. At every step, we produce all possible single-bit mutations of the previous step, and keep only the mutated string that move the string closer or away from randomness. You can see how pushing a string that is composed by a simple substring followed by a random-looking string towards and away from randomness using BDM actually extracts the correct substring. This process of interventions is at the core of the causal algorithmic calculus that we are proposing and is based on algorithmic information dynamics, as applied to, in this example, to strings, before moving to more sophisticated objects such as networks, as we will do. Here is another type of perturbation that minimizes the object shifts towards or away from randomness. We call it neutral perturbation because we maximize the preservation of the main features in the data. You can see how the shorter string in the last step still seems to preserve some of the features of the original string, such as the turns between zeros and ones, but it has been significantly reduced in length. Random data reacts different to guided perturbations. Let S be algorithmically incompressible, that is algorithmic random. This means that S has no generating mechanism shorter than the string itself and can only be generated by a computer program of the type print S, which is not much shorter than S itself. Let S prime be the result of negating any bit in S, just as we did in the previous example. Then we have that the new computer program producing the mutated version is, just as in the previous example, print S prime. There are two possible relationships between the original computer program and the new one after a single bit perturbation, or bit negation. Either one is shorter than the other, or they are equal depending on S moving towards, away, or not moving S at all, respect to the complexity of S. However, perturbing only a single bit cannot result in a much less random S prime, because we are only applying a bitwise change to the original string, and we can always account for that change with a very small computer program that can use actually the original computer program printing the original S. But S was random, and the bitwise operation is fixed and of a small length, and so the operation actually does not contribute to the already high algorithmic complexity or randomness of the original string, contrary to the original assumption that S is algorithmically random or not compressible. So all perturbations in a random string or a random object look like neutral because they don't really make much difference when applying them to an already random object. This means that perturbations to an algorithmically random object have a lower impact on their new candidate generating mechanisms or lack thereof than perturbations to non-random objects with respect to the generating mechanisms of their unperturbed states. And thus, this effect can be exploited to estimate and infer the causal content of causal and non-causal objects. In an algorithmically random object, any change goes unnoticed because no perturbation can lead to a dramatic change of its already high algorithmic complexity or algorithmic randomness. Real-world cases will move in an intermediate region between determinism and randomness. The principle on which this causal calculus and algorithmic information dynamics is based on is the principle that we have already mentioned before, the principle of the conservation of algorithmic complexity in deterministic isolated systems evolving over time. In other words, the rate of algorithmic complexity change is constant and changes by at most a very small logarithmic term as a function of time when time is needed to specify a particular state. Otherwise, the algorithmic complexity of such a system is always exactly the same because it is all generated by the same computer program. Here, for example, is the elementary cellular automaton rule 30, which is deterministic and once started with an initial condition can be isolated. No matter where the evolution stops, the algorithmic complexity of the cellular automaton is always the same, as the rule has never changed, and only the time is needed to reproduce exactly the same object. So after 1 step, 2 steps, 100 steps, or any number of steps, the algorithmic complexity of the object remains the same, except for the logarithmic term accounting for time, that for all purposes can be neglected. But if a system is perturbed from the outside, and such a perturbation cannot be explained by the system's rules, then the algorithmic complexity of the system from that point on will be different or will suffer a noticeable change at that precise point in time. So we can know important information by detecting every time that the system deviates from its normal course. It is perturbed or any of its parts behave random, precisely by looking at how removed it is from the conservation of its algorithmic complexity. Networks can be seen as generated by computer programs too. Here on the left we have some examples of computer pseudocode able to describe the networks on the right, and we can see how applying perturbations to the network on the right, such as deleting an edge or deleting a node, would have changes in its generating candidate models on the left, depending on the algorithmic complexity of the network. For example, in a complete graph, deleting a node does not change the generating mechanism because the resulting graph is still a complete graph, and we can regenerate the original graph with exactly the same computer program with no need to make any modification to the program. However, in a random graph, one in which the description of every edge is necessary to describe the network, every change to the network produces a significant change to the computer program that describes it. Yet, such a change at the level of the computer program is small compared to the long length of the computer program describing the original random graph, and so the model remains of almost the same length, even when it suffered a significant change. Finally, when the network is neither trivial nor random, we have that the computer program is of a small size, but modifications to the data, in this case the network, would require a major change on the explaining model, candidate model. This means that by having a rough estimation of the complexity of the original object and performing perturbations on the object, we can tell apart trivial and random cases from complex cases by seeing the effect of perturbations on the generating model. In this way, we can color every element of a network by its contribution to its generative model, just as we said before. In a complete graph shown in figure A, all nodes are neutral because they have no noticeable effect in the generating mechanism that can regenerate the graph when nodes are removed, because the original and mutated graphs are still both complete graphs. But randomly removing an edge from a complete graph produces a major effect in the model, explaining the original graph, so all edges are colored in red in figure B, because the removal moves the object towards randomness. This is because when you apply a perturbation to an edge in a complete graph, you have to use the original model plus account for the edge that was removed. So the original generative computer program changes significantly. In a random graph, like the graph in figure E, all nodes and edges have very little effect in the original long model explaining the random graph. And sometimes in less trivial and non-random graphs, some changes move the graph towards simplicity too. For example, by removing colliding edges from an otherwise unidirectional path graph, as in figure D, would move the network towards simplicity or away from randomness. And that's why it is colored in blue. But in fact, we do not have to color elements in binary or trinary with 2 or 3 colors only. We can do it with all the color spectrum and have a more finer grained picture of the way in which perturbing every element in an object, such as a graph, would change the causal properties of the graph, as dictated by its underlying generating mechanism and how it changes according to different perturbations. And we can classify networks by whether they are blue or red shifted, meaning that most elements of a graph can move the graph towards or away from randomness, giving us a vector of interesting features that effectively provide a ranking of the ways in which an object can naturally or artificially be moved. The spectra can also be plotted as a curve that we call an information signature, and we will denote by sigma and the name of the graph, in this case G. The information signature consists in ordering the element values from positive to negative contribution to the original object. Positive elements move the object away from randomness, while negative elements would move it towards randomness. Different graphs have different characteristic signatures. For example, in a perfect algorithmic random graph, all elements will be neutral, but in pseudo-randomly generated random graphs, elements will accumulate around 0, with most of the standard deviation on the positive side, and then a small negative tail. This is because, in general, it is easier to move a random graph away from randomness than further to randomness if we assume that the graph was already random, or at least we try to generate it in that way. In a simple graph, however, such as a complete graph or a fully disconnected graph, all elements, such as nodes, would be neutral, and therefore the signature would be a constant at 0. And finally, complex networks will have elements on both sides, and if they produce an edgy inverted S shape, it can be considered to be critical, because basically any perturbation changes dramatically the nature of the object and moves it towards or away from randomness immediately. Notice also that while these critical graphs can exist for algorithmic probability, they cannot exist for measures such as logical depth, because dramatic changes of logical depth by changing only one element at a time are impossible. This is because of the so-called law of slow change of logical depth, coming from the fact that one cannot shortcut introducing a lot of computation to either increase or decrease the logical depth of an object in a few steps. So now we can ask whether moving these networks in the algorithmic complexity space can move them in any other way in an educated or predictable way. Questions such as what kind of topology is changed or preserved when pushing or pulling objects towards or away from randomness are very interesting, and what would tell us to move networks on the algorithmic complexity space, if such networks had dynamics on them, such as Boolean networks, would be also very interesting. So we will try to answer these questions in the next lessons. Here are some examples of the way in which we can numerically move networks with algorithmic information dynamics and our causal interventionist calculus. In figure A, for example, is a complete graph, denoted by K, that is pushed away from randomness by edge deletion and produces other complete graphs after 10 and 19 steps, respectively, starting from the complete graph with 10 nodes. And this was exactly what it would be expected to happen exactly at these steps, because we are precisely removing edges from the same node to push the network towards the next simple network. In figure B, we show an example of pushing a network towards randomness, as it would have been expected. The result of pushing a complete graph towards randomness produces an Erdős-Renyi graph, approaching edge density equal to 0.5, as it would also be theoretically expected. In figure C, pushing a random graph towards simplicity reveals a structured subgraph after 32 and 41 steps, contained in the original random and revealed by pushing the network towards simplicity. In the next unit, we will start with examples to show how we can reprogram networks, not only in this sense, but how moving them in the algorithmic complexity plane actually make systems provided with some dynamics to behave in different and rather controlled ways.